Okay, so I'm going to go through this pretty nice and quickly and explain my work. I have everything written out here for you guys. So, yeah. All right, so for number one, remember the formula for mass percent is mass of solute divided by mass of solution. And remember, to find the mass of the solution, it's just the mass of the solute plus the mass of the solvent. So here I give you the mass of the solute, which is sugar, and I give you the mass of the solvent. So what you need to do to calculate mass percent, you need to take the mass of the solute, which is 41.2, and divide it by the mass of the solution, which is the 41.2, your solute, plus your solvent. Multiply it by 100, make sure you have the correct number of sig figs, and I get 7.64%. Okay, for number two, it's a little bit funky. I'm giving you mass percent in this case, and the mass of the solvent. So you need to plug in everything. So remember, this is your formula. I don't know the mass of my solute, so I make that X. I put that over 315.2, which is the mass of my solvent, plus the mass of my solute, which is unknown, so I make that X, equals, remember, this is a percent, and in order to use it in your formula, you need to move your decimal place over two places. So 1, 2, because you've divided by 100. Okay. Now, to solve for X, what I have to do is cross multiply. So I'm going to do the 315.2 plus X, and I'm going to multiply that by the 0.153. And I'm going to set that equal to the X times 1, which is just X. So here I've got it up here, X equals 0.153X plus what I got from multiplying the 315.2 by the 0.153. Subtract both sides by the 0.153X, and then divide both sides by the 0.847. And so what I get for X is 56.9, because I'm basing it off of sig figs. So the mass of my solute is 56.9 grams. And then I know the mass of my solvent, which is the 315.2, so the mass of my solution, I just add the two together. So mass of solute plus mass of the solvent. Remember, when I'm adding, in this case, I'm not doing it based on sig figs, I'm doing it based on decimal places. So this is 1 decimal place, this has 1 decimal place, so my final answer needs 1. Okay. For number 3, again, we're still doing the same problem, I'm just changing what I tell you. So I give you the mass of the solute and the mass of the solvent. So the mass of my solution I get by just adding them together. Okay? And it's based on decimal places. So 1 decimal place, 1 decimal place, so my answer needs 1. Then to find the mass percent, what I do is the mass of the solute divided by the mass of the solution and multiply that by 100. In this case, because I'm multiplying and dividing, I need to do it based on sig figs. So this is 3 sig figs, this is 4, so my final answer needs 3. For 4% by volume, same formula as percent by mass, except I'm dealing with volume. So volume of the solute divided by volume of the solution, multiplied by 100, and that gives me my percent. So in this case, I tell you my percent, so I'm going to move the decimal place over 2 places again, right? I don't know the volume of my solute, so that'll be X divided by X plus 21.0, which is the volume of my solvent. Again, cross multiply, and I get this. To isolate X, subtract both sides by 0.132, and then divide by the 0.868, and I get this answer. Now, since I'm dividing, okay, I'm going to base this off of sig figs. So the fewest number of sig figs is 3, so here's my answer. Okay. Now, to find the volume of the solution, I just need to take the volume of the solute plus the volume of the solvent. And since I'm adding in this case, I'm going to base it off of decimal places. So this is 1, this is 2, so my final answer needs just 1. Yeah, adding-wise, it's kind of funky because these two don't actually add up to this. I'm rounding, but it's okay. All right, the next one I'm doing molarity, which is moles of solute divided by liters of solution. I'm given my molarity and I'm given my number of moles. So what I'm going to do, set this equal. So here's my molarity here. X is on bottom because I don't know the volume, and there's my number of moles. So I'm going to cross multiply. The 0.512 times X equals the 0.325. To isolate X, I need to divide by 0.512, and I get my answer, which is 0.635. And the reason why I did that was because I want 3 sig figs, and it's liters of solution. So make sure you're doing correct number of sig figs, and you're putting in the units. All right, for here, what I'm doing is I'm taking a volume of a sample, okay, and it's 122 mils of this 1.2 molar solution, and I'm diluting it. So as soon as you see the word dilution, or you're seeing 2 different volumes or 2 different concentrations, automatically you should be using this formula, M1 V1 equals M2 V2. So here's my V1, this is my first volume, and this is the concentration of it. And what I'm trying to do is find the concentration that would be of this volume. So 122 times 1.2 equals the molarity of the 500 ml solution. So you divide both sides by 500, and I get 0.29 because I want 2 sig figs. And this makes sense, right? If you take 122 ml solution and add enough water for it to be 500 mils, the concentration should be less than what it started at, which was 1.2. Okay? Next one, describe how you would make a 2.5 liter solution of, oh, and notice I changed this. This is going to be a sig fig issue, so 2.500 liters of your 0.1 molar solution if I start with a 5.5 molar solution. So in this case, guys, I'm taking a concentrated solution and trying to dilute it. So I'm going to start out, say, okay, I want 0.100 molar solution. I want 2.5 liters of that. How much of this will I need? And so M1V1 equals M2V2. I'm solving for how much of the 5.5 molar solution I need. So I solve it, and I get 0.045 liters of the 5.5 molar KCl solution. So this is what I need to measure out first. And then I'm just going to add water to get this final volume of 2.500 liters. So what I do is I just add 2.455 liters of water. And I've got this solution now. I've got this volume, and I've got this concentration. And you're done. Super easy. Number 8, to what volume should you dilute 25 mils of a 12 molar solution? So this is V1, M1, to obtain a 0.500 molar solution, so that's your M2. So plug it in again. 12 times 25 equals 0.500 times your volume. So I'm going to solve for volume. What you get is 600 mils. Now, keep in mind I want 2 sig figs, so this is where it gets a little bit tricky. 600 only has 1 sig fig, so I'm going to move my decimal place over 2 places, 1, 2, make it into scientific notation, which is that 6.0 times 10 to the second. Now I've got 2 sig figs. And make sure to put units, which is milliliters. Okay, for here, suppose a vodka martini contains 30% alcohol with the remaining portion of the drink composed of water. So water's your solvent always. When in doubt, water's your solvent. So alcohol would be your solute. Okay. Polar molecules dissolve other polar molecules, and ionic compounds, while nonpolar dissolves nonpolar. So like dissolves like. The solubility of solids in water decreases with increasing temperature. When you make hot chocolate, the reason why it's hot is not because it's cold. The reason why is because you want it to dissolve as much chocolate as possible, so you increase temperature. Okay. The other thing that increases the solubility of solids in water is agitation, so stirring it. Okay. The solubility of gases in water increases with increasing pressure, right? So that's why when you open a bottle for the first time of soda, you hear a huge hiss because there's a lot of pent-up pressure, which the companies put in to make sure that the gases stay soluble in the water. The other way to increase solubility is actually to decrease temperature. So that's the exact opposite of solids. So it's kind of funky, but something to keep in mind. A solution is saturated with N2, which is a gas, and Na, which is a solid. When the solution is cooled, so we're cooling it, which means the gas would become more soluble, but the solid would become less soluble because their temperature has a different effect on gases and solids. So B, the sodium iodide would precipitate out, and that's because solids are less soluble when it's cold, while gases are more soluble. When it says it would bubble out a solution, that means that it's less soluble. So that wouldn't happen because the gas actually becomes more soluble. All right, we dissolve this amount of sugar in that. What is the percent, the mass percent? So we've got, this is our solute divided by the mass of our solution. So we've got to add these two together and multiply by 100. So A is your answer. And guys, I need to be seeing this amount of work for every problem, even if you can do it in your head. Because if you don't show it, if it requires a lot of math, I'll take off. If it requires a little bit and you get it wrong, then I can't give you partial credit. For molarity, it tells you the grams of NaI and the volume of solution. So since for molarity it's moles, I've got to convert this to moles. So grams on bottom, moles up top. Here's the molar mass of NaI, so that's the number of moles. And I divide it by liters, so here's my concentration. So the answer is D. You need to prepare a 2-liter solution of 0.1 molar Na2CO3. The best procedure is to, okay, so I first want to find out how much of this I need. So I need to calculate how many moles of the solid I need. So I'm going to put 0.1 here because that's molarity. I'm going to have a 2-liter solution, so that'll go on bottom, and I'm going to solve for X. What I get is 0.200 moles. But the interesting thing is that you can't just measure out moles in the lab. So instead I've got to now convert it to grams using the molar mass up top, and that gives me how many grams I need. So I need to add this amount of the solid and then add water until its final volume is 2 liters. Because remember, it's liters of solution, not liters of solvent. Okay? For 17, how many milliliters of solution must you prepare? So I know what concentration I want. I know how many moles I need, so I'm going to plug this in. So there's my molarity, there are my moles. I'm solving for X. Now, the answer I get is 0.13 liters of solution, but I'm asking for milliliters. So you need to crisscross swoosh if you have to, multiply by 1,000 because the mils go on top, or just recognize the fact that you've got to move the decimal place over 3 places. So if you can do that in your head, awesome. If you can't, you got to show your work. Okay. How many grams of KCl are needed to make 50 mils of this concentrated solution? Well, the first thing I have to do is make this into liters. So I need to move the decimal place over 3 places, 1, 2, 3. Okay. This is my molarity, those are my moles. So I'm going to first solve for moles, which I did here, and now I got to convert into grams. So I need to use the molar mass of KCl. Okay, and I got A for my answer. Calculate the molality. For molality, I have to have moles of my solute, so I've got to convert this into moles, and I've got to convert this into kilograms, because that's my formula, which you will get on the test. So grams go here, grams on bottom, moles up top. Here's the molar mass of KCl, so I get that many moles. Here, I've got to convert into kilograms, so 1,000 grams on bottom, because kilograms are the larger unit, so I put a 1 in front of them. Okay? And then I'm just going to divide this by that, and so I get this for my molality. And remember, molality, the units are molal, which is little m. Okay? For 20A, what you have to do is calculate molality again, which is almost identical to 19, but then you have to plug it into your formula. So here, I solve for moles of your solute and divide it by kilograms of your solvent. And then I plug that in. So that's my little m, that's my molality, and I multiply that by my Kf, which is 1.86, and I get 1.01. Okay? That's the change. That's a delta T F, which is 1.01, which is my answer. Now, to find the new freezing point, remember it's freezing point depression. So it's going to be that much below the normal freezing point, which is 0. So 0 minus my change in temperature. My new freezing point is negative 1.01. For this problem, the next one I'm asking for boiling point. First, again, solve for molality, which is really nice and easy to do. Plug it in. Your Kb is the 0.512, which will be given to you, times your molality, and I get 0.118. Now, that's my delta Tb. So it's going to be that much above the normal boiling point, which is 100. So it'll be 100.118 because I add it. Remember, degrees Celsius are your units for temperature, and that's it, guys.